Hello students, good evening. Welcome to Get Wallah. My name is Venkatrao. I am teaching Theory of Computation subject. Today is our lecture number 11. Our today's topic is one of the very important concepts of Theory of Computation, that is Pushdown Automata. Pushdown Automata is very interesting topic as well as very important topic for GATE point of view. We will get wonderful questions from this topic in the GATE examination. So today we are going to study Pushdown Automata, all definition of the Pushdown Automata, formal definitions, and acceptance mechanisms, everything. Before going to start, let me recap what we studied in previous sessions. So in previous topic, we discussed about grammar, one of the very important concepts of computer science, grammar. So we studied what is grammar. Grammar is set of rules used to describe strings of a language, that is known as grammar. So, and we have studied definition of grammar, 4-tuple definition, NTPS notation, non-terminal, terminal, production, starting symbol. NTPS notation of the grammar we studied. Then if a grammar is given, how to perform derivation, how to construct derivation trees, that is parse tree, that thing we studied. Then leftmost derivations, rightmost derivation, and types of grammars. One of the very important concept that we studied in the last class is types of grammars. Here we studied 4 types of grammar in this. 4 types of grammar, that is type 0, type 1, type 2, type 3. Type 0 is called as unrestricted grammar, type 1 is called as context sensitive grammar, type 2 is called as context free grammar, type 3 is called as regular grammar. So all these concepts, the rules of this, what is type 0, how the rule of that grammar, what is type 1, what is the rule of that, type 2, type 3, their rules we studied, and we have taken some example grammars we performed this type analysis on these grammars. Just construction of the grammar is not sufficient here. If we construct a grammar, that's all. If we think our task is over, then that is not the way. Once the grammar is constructed, we have to identify type of that. That grammar comes under regular grammar, context free grammar, context sensitive grammar, unrestricted grammar. Which type? Once you identify the type of the grammar, then we have to construct corresponding automata for that. Till now the automata we studied is finite automata. We studied finite automata. In that all varieties of finite automata, deterministic finite automata, non-deterministic finite automata, epsilon and fa, those things. The next automata that plays an important role in our theory of computation is pushdown automata. So in today's session we are going to discuss about our important one, that is pushdown automata. So actually in our this total course, this total regular part we have completed. So our thing is context free grammars, pushdown automata. So we are in chapter 2. This is our chapter 2 in our subject theory of computation. Here 2 things are there: context free grammars, context free languages, its corresponding automata. Context free grammars, what type of grammars, what is the rule of the context free grammar, that we studied in last class. Left hand side one non-terminal, right hand side can be anything. In any grammar, left hand side only one non-terminal exists, right hand side anything exists, that grammar is called as context free grammar. So grammar we studied. Now in today's session we are studying its automata. In the next class we will study about its language, context free language. So this is. So here also we studied regular language, we studied finite automata, we studied regular grammar. Last class we have seen regular grammar. So like this 3 things are there in our syllabus of every part. Right. So our today's discussion is on pushdown automata. So let us see. This is the pushdown automata. So the structure of pushdown automata clearly there. This is nothing but finite automata having one stack. Pushdown automata is nothing but finite automata plus stack. Finite automata plus stack. This total structure is comes under pushdown automata. So in this diagram, if you observe only up to this part is finite automata and this is stack. Finite automata plus stack together is called as pushdown automata. This is the general structure. So pushdown automata is not any new thing here. Our known thing, finite automata plus some additional information is there, that is stack information. So finite automata plus stack is known as pushdown automata, right? Now, why we want pushdown automata? Is there any limitation of finite automata? That we have to see. That means we are going to the next level automata, means we are moving to pushdown automata, means there should be some problem with finite automata. There should be some limitation in the finite automata. What is that limitation? Where finite automata fails? Once if you observe this, then we can move to our next thing. So observe some language here. I have two languages, L1 and L2. A power n, B power n, A power n, B power n. A power n, B power n, A power n, B power n. Here one is regular, one is not regular. One of this language is regular, one of this is not regular. When if I provide condition, n value less than or equal to 5, n value greater than or equal to 1. The moment I say this becomes regular, finite automata possible for this. This is non-regular. Finite automata fails for this. Finite automata fails. Here the limitation of finite automata is there. Finite automata fails to accept language L2. Finite automata, both languages seems almost same. Here comparison is there, here comparison is there. Both language looks like same, but in one language L1 case finite automata exists. For L2 case finite automata fails. Finite automata not exist. What is the reason for this? Why finite automata exists one time, why finite automata fails? Because in these two languages we can observe one common property, that is comparison. Comparison exists. Now the question is, finite automata can handle comparison or not? Finite automata can handle comparison. In the initial classes I was saying finite automata fails whenever comparison exists. In that, the default meaning is whenever a comparison goes infinite time. If the comparison required for infinite time, then finite automata fails. If that comparison goes to finite time, then that will be handled by finite automata. This comparison concept linked to memory. Whenever we have a comparison, in order to handle that comparison, memory is required. See, let us take some example. Somebody is comparing with you. So some of your family members say you are not studying well. Assume Just for fun, assume you are not studying well. That means they are comparing you with some other, because somebody may be studying well. So your family members comparing you with that person. If you go in detail, if anybody remembers, your family member remembers other person details, their marks or something, based on that they are comparing. That's why here, whenever there is a comparison, remembrance is compulsory, memory is compulsory. Like this. So previous classes, for so many languages, finite automata, we are unable to construct because those languages having memory, those languages requires memory and having comparison. Like this, whenever any language having comparison, then it requires memory, then finite automata fails. When? If that memory required is infinite time, infinite memory. That's why, so simply don't say finite automata cannot handle memory things. Finite automata can handle memory, that is finite automata. Let me show this in diagram. Whatever this input tape, see this automata, this one or this one, here we have input tape. This input tape is nothing but our memory. Whenever this comparison is going on, we have a states and input tape. This together has to handle this memory concept. In finite automata, we have only this structure, we don't have stack. But whenever stack is included, the size of the stack definitely infinite. That's why stack is considered as a memory element here, memory. So generally in pushdown automata, we can treat this as a memory. It is memory, infinite memory, infinite memory. Here tape plus states together has to act as a memory in finite automata. That's why for this example, memory is required, but that memory is finite memory. For this example, now we'll construct, we come to know how this memory acts. For this example, memory is required, infinite memory. So finite automata handles languages which requires finite memory. Finite automata fails to accept languages whenever that language requires infinite memory. So here infinite memory is required, that's why finite automata fails. Here finite memory is required, finite automata can handle. So what is that memory, how it will be handled, those things we'll study. This is through this example. So this is the failure of finite automata. Whenever infinite memory is required, so this will be keep on goes to infinite time. Right. So finite automata having a stack. Finite automata, this is the finite automata having a stack. This together is called as the pushdown automata. This is our topic, today's topic. Whatever the drawback of finite automata is there, to avoid the drawback, we are adding a stack to the pushdown automata. The stack initially contain something called as Z0, Z0. So finally this total structure, this finite automata plus stack together is called as pushdown automata. In short, I will write it as PDA. Now onwards, in short form, we can call it as pushdown automata, PDA. Good evening. Welcome students. Welcome to today's topic on pushdown automata. Finite automata plus stack, this together, this total structure together is called as a pushdown automata. Right. So here this is our memory. This is our memory. Now this structure, this total structure is capable to handle these languages, infinite comparison like a power n, b power n, It can accept this. A power n, b power m, n not equal to m. All these languages are rejected by finite automata, but accepted by pushdown automata. Language L1 rejected by finite automata, accepted by pushdown automata. Language L2 rejected by finite automata, accepted by pushdown automata. Language L3 rejected by finite automata but accepted by pushdown automata. Like this total structure is having the capability which accepts more number of languages compared to finite automata. That's why if you see the terminology expressive power, we studied name of one terminology expressive power. So the expressive power of finite automata and pushdown automata, whenever you compare, pushdown automata accepts more number of languages. That's why expressive power of pushdown automata always more than finite automata. That's why expressive point of view, if you study pushdown automata having higher expressive power than finite automata. The expressive power of PDA is more than finite automata. It is accepting more number of languages than PDA. This is the overall structure of the pushdown automata. So what is the pushdown automata? The initial definition is finite automata having one stack. That's all. Having stack. The size of the stack is infinite. Remember this point, very important. Size of the stack in the pushdown automata is infinite because we need to handle infinite comparison. Infinite memory is required. This stack acts as a memory. Right. The language accepted by this pushdown automata known as context-free languages. Context-free language. So context-free languages, pushdown automata, context-free grammars, all this is the required subject here. So pushdown automata, the block diagram of pushdown automata, type of language accepted by pushdown automata, these are the things. Structure of the pushdown automata, PDA, structure of the PDA, finite automata plus stack. Then language accepted by PDA are called as CFLs. So this is the overview of PDA. Right. Now let us go and study here in today's session in PDA. The main important thing is construction. We constructed DFA for so many languages. We constructed NFA. Like this, we have to construct pushdown automata. So to construct this pushdown automata, what is the required things? What type of things exist? What type of things not exist? All this concept is we studied through formal definition. So the construction of PDA, if you want to do, then we need to know about formal definition of pushdown automata. What is a pushdown automata? How it exists? Configuration or formal definition. We studied finite automata formal definition. The formal definition of finite automata is like DFA or any finite automata we studied with 5 tuple. This is the definition of finite automata, 5 tuples. Whenever you say finite automata, these 5 things should be there in that. What are those? Finite number of states, input alphabet, one initial state, set of final states, transition function. Like this, whenever we say pushdown automata transition function is having 7 tuple. It is a 7 tuple thing. So here I want to write transition function separately. It's one of the important thing. This is the transition function. So whenever we want to construct pushdown automata, all these 7 things exist or not exist, we have to see. So now we have to construct pushdown automata for some languages. Whenever we are constructing pushdown automata, we have to see whether these 7 things exist or not, and arranging these 7 things in proper order is construction of pushdown automata. Let us see what are these 7 things here. Like in a previous, see, these 5 things are there in finite automata, because pushdown automata is nothing but finite automata plus step. So 5 things. What is Q here? Set of states. Sigma, same as finite automata. Input alphabet. Here Q0, initial state. Only one initial state allowed. Q0 is initial state. Set of states, input alphabet, Q0 initial state, F is set of final states. Order is not compulsory here, you can write in any order. And delta is transition function. These 5 things are over, like finite automata. So as for finite automata, states, input alphabet, initial state, final state, transition function over. Now remaining 2 things are our additional things in the PDA. What is that? Z0 and tau. Z0 and tau. What are these? These are completely belongs to stack. So what is additional concept here? Finite automata plus stack. So initially there is one symbol here in the stack that is called as Z0. So Z0 is called as initial stack symbol. If you see compilers, the main practical application of this one we will see in compilers, parsing algorithms. All the parsing algorithms looks like this structure only. There if you observe, dollars will be there. So in order to identify all the elements of the stack is completed. Whenever we are popping out all the elements completed, in order to perform stack operations, we will maintain initially some element dollar, initial stack symbol. So here that is called as Z0. Z0 initial stack symbol. And then we will push some elements into the stack like this. We will push some elements into the stack, we will pop from. So finally total number of elements present in the stack is called as tau. Tau is stack alphabet. What is the input alphabet? Number of symbols allowed into the input. So if you observe here, symbols allowed into input. What are the symbols allowed here? This is our sigma. A comma B. This is input alphabet. Symbols allowed into stack. See this X not present here, but allowed into the stack. Z0 not present here, allowed into the stack. This is called as stack alphabet, represented with the symbol tau. Represented with the symbol tau. So these are the 7 things. So here the formal definition of PD also, if any students confusing, that is very easy. So here finite automata formal definition, 5 things that is known for us, plus 2 additional things, that is Z0 initial stack symbol, and stack alphabet. Symbols we are pushing, popping into the stack. So finally number of symbols allowed into the stack is called as tau. So this all together, all these 7 things called as our formal definition. In this we have a transition function. The transition function is looking like this. I'll explain you what is the meaning of transition function. See the way of working of the pushdown automata. whenever we have PDA, in order to perform comparison, assume we have this one. Let me change this. This is A, this is B, this is B. I am constructing for A power n, B power n. I want to check number of A's and number of B's are equal or not. Whenever I want to perform comparison between A's and B's, what generally PDA do is, whenever A encounters, we need to remember, we need to perform comparison between A's and B's now. One thing we have to remember. So for every number of A, one X will be pushed into the stack. Whenever PDA reading A, one X will be pushed into the stack. Whenever reading A, one X will be pushed into the stack. Then for every 1B, 1X pop out. 1B, 1X pop out. Like this, B is completed, A is completed, accept. This is the logic of working the PDA. Now we'll construct pushdown automata, then it will be clear. For that reason, PDA takes decision based on three things. Here our states exist. States. Q0, Q1, Q2 states exist here. Here input from Q0 taking some input. This is up to finite automata. But whenever you say PDA, from this state, by reading this symbol, at that time, what is the top of the stack? So based on three things, it will take the decision. It has to perform push or pop. The decision will be taken based on three things. That's why, see the formal definition, visualized like this. PDA decision is taken like this. What is the present state? What is the present input symbol? What is the present stack symbol? Q is state, sigma is input, tau is stack. So based on a given symbol, given input, given stack symbol, for which state we are going on, what is the operation performed in the stack? So this is the formal definition. Based on this formal definition only, we can construct the PDA. Okay. So this is a general overview of the pushdown automata. Its block diagram, its definition. Definition is PDA plus stack. It will accept CFLs, normal definition, formal definition, block diagram. All these are the overview of the PDA. Now, what are the languages accepted by pushdown automata? The language accepted by pushdown automata, context-free languages. Languages accepted by PDA are called as context-free languages. In short form, we'll call CFLs. Now, while accepting these languages, PDA having two methods, two ways of acceptance. While accepting this, it will accept in two ways. Those acceptance methods are acceptance by PDA using final state acceptance method, empty stack acceptance method. Sometimes both final state and empty stack. If you see finite automata, this is the specialty of the pushdown automata. Due to this, so many confusions arises, so many questions also arises in the gate paper in this acceptance method. If you observe finite automata, how the strings are accepted? Final state. By any string, final state is reached, that is accepted, not reached, not accepted. But here the beautiful things in the PDA is, some strings are accepted without having final state. That is called empty stack method. Some strings are accepted without empty stack. That is final state. If it having final state, that is called as final state method. So Final state method is anyhow known thing that is there in all automata. The specialty of this pushdown automata is empty stack. In empty stack method, what is the specialty here is strings are keep on accepted, but final states not there. Without having final states, accepting strings. That's a beautiful mechanism here. So whenever we are practicing questions, so we'll practice both the methods, empty stack, final state, but most of the time in gate papers, we are observing questions from empty stack because it is a specialized one here, right? So this, like this, we have two acceptance methods, keep in mind. One is acceptance by empty stack method. Empty stack method means by reading the string, if you want to accept the string, stack is empty, final states not necessary, no need to have final states. Final state method means by accepting string, now but if you want to accept string in final state method, reaching final state is compulsory, but empty stack is not necessary. Like this, we have two methods, right? Then we have a PDA. If you see the PDA types here, while accepting these methods, PDA having two versions. Non-deterministic pushdown automata, deterministic pushdown automata. While accepting these languages, PDA having pushdown automata having two versions, deterministic version, non-deterministic version. Like finite automata also having two things. In finite automata also we have two things. Deterministic, non-deterministic. But there is a lot of difference in this. The difference is whenever you call the concept expressive power. Whenever you say expressive power, the expressive power of DFNF is same. Expressive power of DFNF is same. Number of languages accepted by deterministic finite automata, non-deterministic finite automata same. But that case is not there here. Here the expressive power of NPDA is more. That means there is a beautiful point here. There are some languages which are accepted by here in finite automata. If a language is accepted by NFA, if and only if it should be accepted by DFA. If a language is accepted by one machine, should be accepted by other machine in finite automata case. But that situation is not there in pushdown automata. There are some languages which are accepted by, I will give example also. There is a language WW power R accepted by NPDA, but WW power R not accepted by DPDA, deterministic PDA. Like this, within the same machine also there are different powers. In the pushdown automata, in the same machine, in its subcategories, we have differences here. That is NPDA having more power than DPDA. That's why generally whenever we mention pushdown automata, the default thing pushdown automata means we consider NPDA. NPDA comes under the general default pushdown automata. Right. So this is the major difference here. So whenever we construct pushdown automata, so we have deterministic pushdown automata, non-deterministic pushdown automata, but the expressive powers are not same. Expressive power of non-deterministic automata is more than deterministic automata, and this deterministic automata is not accepting some of the languages even though they are accepted by non-deterministic automata. So this is the some of the difference we can observe in these two machines, right? So Now the question is, we have acceptance methods, final state method and empty stack method. Is it same for both of these? Acceptance methods are same. Number of languages accepted by NPDA, if it is NPDA case, empty stack and final state, that is L1 by empty stack, L by final state, the number of language concept will be same. Number of languages accepted by empty stack method, number of languages accepted by final state method is same if it is here. All mechanisms are equal. How many languages final state mechanism accepts? All those. That means if a language is accepted by final state, should be accepted by empty stack in NPDAs. But this situation is not there in DPDA. In DPDA, final state, empty stack are different. DPDA using both, they are not same. So in DPDA, language accepted by empty stack, language accepted by final state, not same, not equal. DPDA using final state, DPDA using empty stack is not same here. There are some languages even though accepted by empty stack, not accepted by final state, right? What is then, is there any limitation? Limitation of PDA? Limitation of PDA. There are some languages this is the language PDA fails to accept. It doesn't mean that PDA accepts everything. It is powerful than finite automata, that's all. It doesn't mean that it will accept everything. So it can accept some of the beautiful languages which are not accepted by finite automata, but does not guarantee it will accept all the remaining languages. There is no guarantee like that. So this is what the concept of pushdown automata. So let me recap what we studied. Pushdown automata is a powerful machine than finite automata because it is accepting the language like this, even though these are not accepted by finite automata. Language accepted by pushdown automata is called as context-free languages, which are powerful than regular languages. Generally, these languages are called as context-free languages. So PDA is powerful machine compared to finite automata. Then why this power is coming to this machine? The power is coming to this machine because it is having a stack. What is the size of the stack here? Size of the stack is infinite in pushdown automata, right? What is it? There is a, see, whatever the point I am saying here, from every point, each of these points, there is one question in the gate paper. There is one question in the gate paper from all these points, right? Then we studied formal definition. This is the important thing. The formal definition of PDA having 7 tuple. 5 tuple as it is as finite automata plus 2 things. 2 things are stack. So Q, set of states, input alphabet, transition function, final states, initial state, Z0, initial stack symbol, stack alphabet. All this 7 tuple. Then acceptance methods. We have two acceptance methods, acceptance by final state, acceptance by empty stack. Like this, two acceptance methods are there. So these acceptance methods, in case of non-deterministic PDA, they will show equality. In case of deterministic PDA, they are not equal. So like this. And then we have studied deterministic, non-deterministic natures of the automata. While recognizing languages, PDA having two things, deterministic natures, non-deterministic nature. What is the deterministic nature and non-deterministic nature difference? In a PDA, the non-deterministic PDA accepting more number of languages compared to deterministic PDA. But the difference is not not there in finite automata case. In finite automata, number of languages accepted by deterministic finite automata, number of languages accepted by non-deterministic finite automata is same. Whereas in pushdown automata, non-deterministic machine is accepting more number of languages compared to deterministic machine. So whenever just a PDA is mentioned, pushdown automata mentioned, our default machine is nothing but non-deterministic machine. Okay, this is what the overall introduction regarding pushdown automata. Now let us start construction of pushdown automata for some of the languages which are not accepted by our finite automata. So we have seen limitation of finite automata for so many languages. There are so many languages, those languages are not accepted by finite automata. But all these languages, most of these languages are accepted by pushdown automata. And what is the logic for that? Those things we will study now. Okay. Students, any doubts till now? This introduction regarding pushdown automata is very important. So based on this introduction only, I am going to construct pushdown automata. Pushdown automata construction initially seems bit confusing, but it is very logical, very interesting, very important for examination point of view. So look at this question, construct pushdown automata for the language. Our language is nothing but this is the language. So this is the language I am taking. For this language, we need to construct pushdown automata. So first thing is, if you want to construct, we have to observe the logic. Listen carefully. So the logic to construct this machine, let me write one diagram here. Whenever you are constructing, for you also, taking one rough diagram like this will help you to construct properly. PDA structure, pushdown automata. Start from the initial state. Right. Now what we need to do, number of A's, number of B's equal or not, we need to verify. Our requirement here is how many A's present, for that those many B's present or not. Number of A's and number of B's are equality or not. That equality we are testing here. So what is the logic? Finite this comparison we are for 1A, 1B there are not there. 1A, 1B there are not there. This comparison we are performing. This comparison we have to repeat for infinite number of times. So this situation is not possible by finite automata. That's why we are coming here. So what we will do here is, whenever this automata machine is reading A, that A will push into the stack. If this PDA reads any A, push that A into the stack. Again it is reading A, push that A into the stack. Like this, all A's push into the stack. Let me write the logic here. All A's push into stack. All A's push into stack. Then if B comes, for 1B, like this, all for 1A will be there, 1A. For 1B, 1A pop from the stack. For B's, A's pop from the stack. For B's, A's pop. So this is our final logic. So whenever A's are coming, push into the stack. For B, if there is a A in the top of the stack, pop. For B, if there is a A in the top of the stack, like this. In this way, whenever the B's are over, A's are over in the stack, A's and B's equal. That is the conclusion. Logic is very simple. A's push into the stack. For all A's push into the stack. Whenever B encounters 1B, 1A pop out, 1B, 1A pop out. Logic is very simple. Now implementing this logic through for PDA structure, PDA definition. That is what required for us. Right. All this is through our formal definition. So let me write the formal definition here. The formal definition is this is the formal definition. So let me start from the initial situation. The initial situation is, initially we are in Q0. See, the decision will be taken based on three things. What is our state? What is our input? What is our top of the stack? So initially I am in state Q0. My initial state is Q0. Reading symbol is A. What is the initial top of the stack? These two not there. Initial top of the stack. Initially Z0. So I am in Q0. Reading symbol is A, Z0. What we need to do? What is the operation required? Stack operation. When the logic, then we have to observe the logic. Logic says whenever A is coming in the input, simply push into the stack. So if A encounters, representing this together, so what is there in the stack now? A is pushed into the stack. That's why A is at 0. So this is the configuration of PDA in the initial situation. Let me repeat this step once again. This is the situation of the machine. This is the operation you are performing. Left side comes under situation of the machine, configuration of the machine. Right side is the operation what you are performing. So here initially I am in Q0. My reading symbol is A. My stack symbol. Based on these three things we have to take decision. Your state, your input, your top of the stack. And your going state and your doing operation. We are doing push operation here. Next, what is there? We are in state Q0. Our reading symbol is A. Now top of the stack is A. So now the configuration of the machine is, state is Q0. My reading symbol is A. Top of the stack is also A. This is the machine configuration. Left hand side is the configuration of the machine. Right hand side is what operation we have to do. So then we have to go for logic. What is the logic saying? Logic says whenever A's are encounters in the input, for every A push operation only. For every A, push operation. That's why in the right side we'll stay in the same state. Now what is one more A? Last two symbols if you represent. See, the push operation meaning is if you show these two symbols together in the right side, that is push operation. If you show these two symbols together, that is push operation. Like this, any number of A's, Q0, A encounters, top of the stack A, push. A encounters, top of the stack A, push. Like this, all number of A's will be pushed into the stack. Then what happens? Still we are in Q0, coming symbol is B. Top of the stack is A. That means after some time A's are over, B's encounters. So state is Q0. Whenever B is the input, what is the top of the stack? A. Because whenever B's are over, A's are also top of the stack, always A. Only A's we are pushing. So B comes A top of the stack. Now this is the configuration, machine configuration. State Q0, our reading input is A, B, top of the stack is A. What is the operation? Then we have to look at the logic. The logic says whenever B comes, for 1B, 1A pop. Whenever B's are coming, for every 1B, 1A will be popped out. So now we are moving into Q1. Whenever right side if you represent epsilon, that is the indication of pop operation. So now what happens? We are in Q1 state. State Q1. Now coming symbol is B, top of the stack is A. So the logic I am implementing, what is the logic? If whenever B comes, A is there in the stack, pop that. For 1B, 1A pop. Then we are in state Q1. State Q1, reading symbol is B, top of the stack is A. Q1, reading symbol is B, top of the stack A, pop that. So like this, for every 1B, 1A pop, 1B, 1A pop, by staying in the same state. So loop is going on. I will show this by using transition diagram. These are based on formal definition, normal configuration notation. I will show by using diagram method also. By using diagram, how we will construct this. Like this. Whenever I am in Q0, if sometimes string is ended, we'll read epsilon. So that is this epsilon. Either input, from the input, sometimes we'll read symbol, sometimes epsilon. If it is epsilon, epsilon means what? We are reading B. For 1B, 1A pop out, 1B, 1B. Like this, B's are ended. Tell me logically, whenever in the input B's are ended, what is remaining in the stack? Whenever B's are ended, what is remaining in the stack? Definitely Z0. So 1B, 1A pop out, all these A's also popped out from the stack. So whenever B's are ended, Z0. Then acceptance. This is the situation where we have to say that number of A's and B's are equal. We have to accept. If you want to accept, two methods. Final state, empty stack. If it is final state, immediately go to final. Make Z0. Acceptance by final state method. We can do for empty stack also. Let us see for another example for empty stack. So this is the PDA, perfect PDA. So construction of PDA is, there is no greatness in this. The greatness is there in making this logic. So the greatness is there in this logic. That's why based on your language, initially we have to make one logic. Once your logic is a proper one, then we can construct a PDA in a very nice way. Very perfect PDA we can construct. That's why whenever you see the language, construct one of the logic properly. Right. So here 5 transitions are there. Writing these transitions is very easy based on our transition function. So based on this one, I am writing the transition. Writing transitions based on the logic is PDA construction. So whenever you know the logic, represent that logic by using transitions. This is the pushdown automata, right? So in this, what is there? First two are representing push A's. Push A's into stack. Second two transitions are there for pop A's from stack. So first two are there for push operation representation. These two are there for pop operation representation. Last one is accept. Accept. So like this, whatever our logic is there, that logic representing by transitions is PDA construction by transitions notation. We can show pushdown automata in two notations. One is a transitions notation, other is a transition diagram notation. So now I will show you the same thing by diagram notation. All of you students, whenever you are studying this, generally if we are studying first time, confusion is common, because this to habituate these concepts takes a little bit time, but recording is available. Now what you will do, construct by your own. Wherever you are feeling difficulty, watch the recording, how I am constructing, replicate it, then it will be easy for you. So here main thing is logic. Based on the logic we can construct very easily, right? Now let me construct the transition diagram. Transition diagram. What is the first logic? Start from Q0, the same previous one, first one. From Q0, A is the input, Z0 top of the stack, push. Going to A is the input, stack is Z0. From Q0, A is the input, top of the stack is Z0. What is the operation? Push operation. So show them together. This is indication of push. So like this, every transition one by one will represent. What is the second one? From Q0, input is A, top of the stack is also A. Input is A, top of the stack is A. Going state is also Q0, push operation. From Q0, input is A, top of the stack also A. Going state same, push operation. Like this. First transition, second transition. From Q0, A is the input, top of the stack is Z0, push. From Q0, A is the input, top of the stack is A, push. Third one. From Q0, B is the input, A is top of the stack, then Q1. From Q0, B is the input, top of the stack is A, then Q0. Perform pop. Transition for this one. From Q0, B is the input, top of the stack A, go to Q1, pop. Then for this transition, if we show in diagram, from Q1, B is the input, top of the stack is A. go in the same state, pop. Look at this. From Q1, B is the input, top of the stack is A, going to same Q1, self loop, same Q1, then perform pop. What is the last one? From Q1, epsilon comes, top of the stack is Z0, accept. From Q0, epsilon comes, top of the stack is Z0, accept. Go to the final state. Transition diagram. Why we have to show both the notations, transition diagram and transitions notation, is in the gate paper sometimes they will construct pushdown automata by using this. Sometimes they can construct pushdown automata by using previous. So we need to have it with. Sometimes in the paper, in the gate papers, sometimes pushdown automata can be given by this notation. Sometimes pushdown automata will be given by using this notation. That's why you need to practice both. For a given language, the way of construction of pushdown automata by diagram method, by transition method, both methods you have to be perfect. Okay. So this is about construction of pushdown automata. This is a basic problem. So in coming classes, we'll construct some of the very logical and important concepts of pushdown automata. See, the major thing here in pushdown automata is logic. So whenever you want to construct any pushdown automata for any language, first you should know logic of that. So here first we made a logic to accept this language A power n, B power n. We made a logic. Representing that logic by transitions or transition diagram is very easy. So initially, the moment we see any language, try to make one logic to accept that language. Okay. So still, if anybody having any confusions over this, watch the recording once. Watch recording, construction of pushdown automata. The coming classes also will construct pushdown automata for so many interesting languages. Then you can ask me if you have any doubts. Okay guys, that's all about today's session. Thank you. See you in next session.